Okay, this is probably more likely to come up on a test than an actual just a mathematical problem. It's probably more like a relationship problem, meaning how does one thing relate to another. And so what we have here is the electromagnetic spectrum, and this is all different types of things that are in the electromagnetic spectrum. And so what we can see with our eyes is right here, visible light. Okay, so the only thing that we can really determine are going to be things in the visible light range. And so there's a lot more going on than that. There are radio waves and microwaves and infrared and a lot of things you just can't see, even though they are moving about your house, moving around. There's UV rays, not a lot of X rays, but there's a lot of things that are moving around. And so, in the visible light spectrum, you got your Roy G. Biv, so that's your red, orange, yellow, green, blue, indigo, violet. That's the colors of the rainbow, right? And so that's how you can kind of remember them. So the long wavelength one is red, and then violet is the short wavelength, and then they are kind of intermingled inside there. So we want to know this relationship between what we're going to call wavelength, energy, and frequency. So I talked about that earlier. So a gamma ray, all right? So gamma rays, we want to remember that gamma rays are a little bit more dangerous. They are the things that you're worried about with nuclear weapons, a nuclear bomb, a reactor, a nuclear reactor, or superheroes, right? So, like the Incredible Hulk was created with gamma rays, so they have to be dangerous. Spider-Man was created by a spider that was affected by gamma radiation, right? So we know that if you come into contact with this stuff, you might get turned into a superhero. And so this stuff is not to be messed with. Probably should have made the Hulk in green, but whatever. So there we go. So a gamma ray is going to have and we have these two blanks here. It's going to have a low or a short wavelength. So let's go ahead and write that in there. And it's going to have a high frequency. And so a short wavelength and a high frequency, okay? And this is high energy. So these are high energy. And so what you have to know for the test is that frequency and energy are the same thing. They are a direct relationship. If you have a high frequency, you have a high energy. Okay, so they're going to go hand in hand. Where wavelength is the opposite. Whatever happens to energy, whatever happens to frequency, wavelength is going the other way. So you have a very small wavelength, you have a lot of energy. What that means is lots and lots and lots of waves are hitting something over a short amount of time. So that's a lot of frequency because you have such tiny, tiny waves, right? Now, if we go down to the bottom, the opposite. So up here we've got gamma rays, so dangerous stuff. Down here we got radio. Radio is not dangerous. So those are going to have long wavelengths. So we'll use the red for the infrared, which is also long wavelengths. And it's going to have a long wavelength, and then it's going to have a low frequency or a low energy. Might want to put a small, I think small frequency, because these are often numbers. So you can see they're just opposites, right? So now I can kind of look at the things on here. So infrared, that's what controls your remote control at home. Like if you've got a television, obviously you probably know what a microwave is. Television waves, radio waves, these are big and they're not dangerous. And then well, we know that ultraviolet rays and tanning in the sun is not particularly good for you, and so that is in the higher energy area. And then of course X rays, and then the gamma rays. So if we slide down here, I've got a graphic, and so you can kind of see some of the concept. And this is I don't think this is in your specific note packet. And so radio waves are like the size of buildings in terms of their wavelength. They're huge. Where gamma rays, their wavelength is the size of an atomic nucleus. It's tiny, 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 tiny. And so things that have really small wavelengths, size of atoms, size of molecules, amoeba, protozoans, whatever, needles. So you can see that now we're getting bigger and bigger. And so as the wavelength gets bigger, then the energy associated with it is not as dangerous. And so basically what happens is if you have something that has a lot of energy, it's because there's a lot of these waves hitting in a single place. And so it's happening over and over and over and over again. So it's a lot of frequency, so frequent waves, and that's a lot of energy. So please keep that straight. This relationship right here between wavelength and frequency, that's something you really need to know for the test. And so that is something that I would denote as important. So this relationship, these are important, okay? All right, so now we slide down here. You can see just, some more of the same kind of stuff, energy, wavelength, etc. So let's slide over. Now we're going to talk about the atomic emission spectra. So this is going to be a little bit more terminology, some things like that. What we've got here is the atomic emission spectra of hydrogen, or really of any element. And so what we're talking about is basically a chemical fingerprint is created by all the elements. So if you put energy into an element, it's going to give energy back, and the energy it gives back is very specific. No element has the same energy spectrum that they give off, okay? And so to understand this, you've got visible or white light, which creates a continuous spectrum. So a continuous spectrum is what we would consider a rainbow, where you have all of the colors, right? So when you have a rainbow, you have all of the colors, and it's not like you look at the rainbow and you're like, hey, wait a minute, where's the red? Well, no, so all the colors are there. And so that's a rainbow where there are no breaks in the color. So we'll write that down. That's the idea of continuous. So where there are no breaks. Okay. So that's continuous, right? So that's normal light, that's continuous. But then if you heat up a specific element, it will give off what's called a line spectrum. Okay, so the line spectrum is unique to each element. So every element has its own line spectrum. So if you come down here, it says the lines are unique for each element. Each element gets its own specific line spectrum. So they are discontinuous. So discontinuous means that there are going to be gaps, okay? So you're going to have lines and then gaps, and the gaps are going to be dark regions. So you're going to have colored lines and dark gaps or spaces. And I'll show you one of these here in a minute. Okay, now it says that when you look at one of these right here, it says, note, many of the lines of the spectrum are not visible to the naked eye because they are in the ultraviolet or the infrared regions. So we can only see parts of the line spectrum that our eyeball can see. But what happens is that there are other parts that we can't see. So let's go take a look at the next page. We'll come back to that other thing. So here we go. I'm going to zoom in even a bit more. Right there. So there's a line spectrum. And so that first line spectrum, that's for hydrogen. So hydrogen gives off specifically those lines. So 1, 2, 3, 4 tiny, 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 tiny parts of the entire rainbow. So that's like you look at the rainbow and then a bunch of the rainbow is missing. Okay, and then helium does the same thing, except for, see, there's different lines. And so helium here is going to have different lines, and that's what makes it unique. So this is a fingerprint. So this is a unique identifier for these, and they give these off. Now, I'm going to show you a quick video on this. Now, we're going to mute this a little bit because I don't think you need the sound, but we'll kind of go through this and I'll kind of talk through it. So this guy is basically going to play with a spectrometer. And so right here with this light, that's the continuous spectrum. So if we look at that, that's the whole rainbow. So that's white light. He's diffracting it, and it's giving us the entire spectrum. So that is the entire spectrum. There's no break to it, and that's what white light gives you. It gives you a rainbow. So you don't look at the rainbow and you're like, hey, wait a minute, I don't see one of the colors. It's missing. No, that's, you get everything. So that's called a continuous spectrum, right? So there's the continuous spectrum. So let's slide forward a bit. And so here, this is mercury. And so this is the spectrum for mercury. So inside there, they've heated this up. The mercury is giving off a very specific light. And when you take and you diffract it, you'll see that it creates some specific lines. So those are very specific lines it's giving off. So it's giving off that blue and that green line. But you can see that unlike the rainbow, it's missing all kinds of pieces, right? Like there's no red, there's no orange. It's missing a bunch of the pieces. So go back to that for a minute. That is it's discontinuous, meaning it's missing pieces. So that's the line spectrum over to the right and left. It's the same thing on the right and left. It's just mirror images. And so that's kind of what it gives off that we can see. Now, if we slide down here, then here's another one. You can see that we are giving off different pieces of the rainbow. Once again, there's some blues, some greens, some oranges, some reds, a lot more of the rainbow, but still missing pieces. And once again, this is unique to each element. And if we slide down here, then this element here is giving off really only reds and oranges, maybe a tiny bit of green, missing the blues, things like that. And then this is hydrogen actually here, which is the one that IB always focuses on. And so then these are the specific lines that hydrogen gives. And you can basically, you get to see 4 of them out of the entire rainbow. So 4 tiny pieces. And so this is the idea. Now, I used to do this in class, but what happens, we always burned up the bulbs, because if you leave the bulb on very long, it burns it out. So I think that this gives you an idea of what we're talking about. Once again, you have to have the bulb, and then you also have to diffract the bulb. And so that's kind of what he's doing here in the demo. So I thought that would give us kind of give us an idea of what was happening there. So, all right, so we're going to go back